Hello everyone, we start chapter 8, which is about relations, and we started with section 8.1 and an example which is about less than relation for real numbers. So as you remember, we defined relations in chapter 1, but here we are going to explain some properties of relations and more examples. So consider example 8.1.1 of the book, which basically says let's define the relation L from the set of all real numbers to the set of all real numbers. So both the domain and codomain in this example is the set of real numbers. So we define L as follows. We say for every real number x, for every real numbers x and y, we say x is related to y by L if and only if x is less than y. So for example, 57 is not related to 53 by R because 57 is greater than 53. However, minus 17 is related to minus 14 by relation L because minus 17 is less than minus 14. In a similar way, we can say 143 is not related to itself by relation L because 143 is equal to 143, and similarly we can say negative 35 is related to 1 by L because negative 35 is less than 1. So this is a very simple example of relation from the set of real numbers to the set of real numbers that we all are familiar with and we use it every day. Okay, so after that simple example, let's define the inverse of a relation. So consider R as a relation from A, which is the domain of R, to B, which is the codomain of R. Then the relation R inverse from B to A can be defined by interchanging the elements of all the ordered pairs of R. Let's define it formally. Let's define the inverse of a relation formally. We say if R is a relation from A to B, then we define the reverse of relation R from B to A as follows. So basically B, which was the codomain of R, becomes the domain of R inverse, and A, which was the domain of R, becomes the codomain of R inverse. We say R inverse is equal to this set, the set of all ordered pairs of y and x belongs to B times A, or B cross product A, such that x and y belongs to R. So if we want to say this definition in an operational way, we can say for every x belongs to A and y belongs to B, we can say the ordered pair of y and x belongs to R inverse if and only if x and y belongs to R. So if R is a mapping from set A to set B, R inverse is a mapping from set B to set A with the opposite direction. So let's see an example of the book, example 8.1.4. Okay, so let A be a set of three integers 2, 3, and 4, and B be another set of integers 2, 6, and 8, and consider R as the divides relation from A to B. So more precisely, we can define it in this way. We can say for all x and y, ordered pairs x and y belongs to A times B, or belongs to the cross product of A and B, we can say x is related to y if x divides y. So R denotes the divides relation. Now, here's the question. We say the question is state explicitly which ordered pairs are in R and which ordered pairs are in R inverse. Okay, so if we wanna write down the relation R, we need to find out which element in A divides which element or which elements in B. For example, 2 divides all the elements of B, right? Because all the elements of B are even. However, 3 as another element of A only divides 6, and 4 only divides 8. So we have a total of 5 elements for relation R. The first one is 2 and 2, then 2 and 6, 2 and 8, 3 and 6, 4 and 8. So as a result, we can conclude that R inverse has the same number of elements. Why? Because every element in R, every ordered pair in R corresponds to another element in R inverse. Basically, we need to reorder that ordered pair to get the corresponding element in R inverse. So as a result, we can say the following elements are in R inverse. 2 and 2, correct? So I can create the correspondence relation between these two members, and then 6 and 2, which corresponds to 2 and 6 in R, then 8 and 2, which corresponds to 2 and 8, 6 and 3, which corresponds to 3 and 6 in R, and finally 8 and 4, which corresponds to 4 and 8 in R. So as you see, we have these 5 ordered pairs in R inverse. Okay, so here we give another definition. We say a relation on set A is a relation from A to A. So if the domain and codomain of a relation are the same, instead of saying that the relation is from domain to codomain, we basically say the relation is on that set. So here we use the word on instead of saying from to. Why? Because domain is equal to the codomain. So instead of saying from the domain to the codomain, we basically say a relation on a set like A. So let's see another example which basically introduces a way of representing a relation using a graph. So for example, if A is a set including integers 3, 4, 5, 6, 7, and 8, and if R is a relation on set A, which is defined in the following way, for every x and y belongs to A, x is related to y by R if and only if x minus y is even, or 2 divides x minus y. So for this relation, we can draw the following directed graph basically we draw one vertex for every element of set A. So since set A has 6 elements, we have 6 different vertices in this graph. We have vertex or node 3, we have node 4, we have node 5, 6, 7, and 8, correct? And then for every element in the relation, we need to draw an edge from one vertex to the other vertex. How? For example, since 3 and 5 are related to each other, so we draw this vertex, we draw this edge from 3 to 5. In a similar way, since 3 and 3 are also related by R, so we draw a loop from 3 to itself, which represents the member of 3 and 3 in relation R. As you see, in the similar way, you can justify all the edges drawn in this graph, and the whole graph represents the relation R on set A. Okay, so here we define 3 very important properties of a relation: reflexivity, symmetry, and transitivity. The first property, which is reflexivity, is defined as follows. We say a relation R on a set A is called reflexive if and only if for every element X belongs to A, X is related to X. Or in other words, we can say each element is related to itself. That means that relation is reflexive. Now let's focus on symmetric property. We say a relation R is symmetric if and only if for every X and Y belongs to set A, if X is related to Y, then Y is related to X. That's called the symmetric property. In other words, if any element is related to any other element, then the second element is related to the first. In the third property, which is transitivity, we basically say R is transitive if and only if for every 3 elements X, Y, and Z belongs to A, if X is related to Y by R and Y is related to Z by R, then X is related to Z. So you can see this relation X and Y right here, and relation Y and Z right here. So if we have these two relations, then we should have a relation from X to Z. That's called the property of transitivity for a given relation R on set A. So basically it means that if any one element is related to a second and that second element is related to a third, then the first element is related to the third. That's called the transitivity property of a relation. Okay, so here we see an example of the book regarding the properties of relations. Consider A as a set of 4 integers 0, 1, 2, and 3, and consider R as a relation defined in the following way. We define R as a, using a set roster notation. It contains a number of ordered pairs. The first one is 0 and 0, then we have 0 and 1, 0 and 3, 1 and 0, 1 and 1, 2 and 2, 3 and 0, and finally 3 and 3. The question is R reflexive, is R symmetric, and is R transitive? In order to answer to these three questions, it's better to first draw a directed graph representing such relation. So in this graph, we need to have four vertices, one for 0, the other for 1, the other for 2, and finally one for number 3. And then for every ordered pair, we need to draw an edge from one vertex to another. So 0 and 0 is represented by this edge. Then we have 0 and 1 here, 1 and 0, 0 and 3, 1 and 1, 2 and 2, 3 and 0, which is here. This is 3 and 0, and finally 3 and 3, correct? So the first question is R reflexive? And the answer is yes, because as you see here, there is a loop at each point of this directed graph, which means that every element of A is related to itself by relation R. In the similar way, we can claim that R is symmetric because in each case where there is an arrow going from one point of the graph to the second, we can find another arrow going in the opposite direction from the second point back to the first point. For example, here from 0 to 1 we have an arrow, and then we have another arrow in the opposite direction from 1 to 0. Also, we have an arrow from 0 to 3, and also we have another arrow from 3 to 0 in the opposite direction. So whenever there is an arrow from one vertex to the other, there is another arrow in the opposite direction. So that's why we can claim that R is symmetric. The last property and the last question is that is R transitive? And the answer is no. Why? Because considering this figure, we have an arrow from 3 to 0 and an arrow from 0 to 1. So if we will have transitivity for relation R, we should have a relation from 3 to 1, or an arrow like this. But we don't have. Also, since there is a relation from 1 to 0 as 0 to 3, we should have another arrow, this time from 1 to 3, like this. But we don't have any of these two arrows in the relation, so we can conclude that R is not transitivity. We basically disprove the transitivity property of R by giving a counterexample. Okay, so after defining three different properties of a relation, here we define an equivalence relation. We say if A represents a set and R represents a relation on that set, we can say R is an equivalence relation if and only if R has all of these three properties: reflexive, symmetric, and transitive. So if R is reflexive, symmetric, and transitive, we can claim that R is an equivalence relation. So let's see an example of an equivalence relation. We know that there is a relation on R which is the set of all real numbers, uh, which we call it the relation of equality. It basically says any two real numbers x and y are related, or we can say x is related to y if and only if x is equal to y. That's called the relation of equality among the set of all real numbers. So this relation is obviously a reflexive relation because any number is uh, equal to itself. So basically any number is related to itself by the relation of equality. And then it's obvious that this relation is symmetric too, because if uh, one number is equal to another, we can say the second number is equal to the first number too, because equality has no direction, is a bidirectional relation. And finally, we can say the relation, the equality relation is transitive too, because if x is related to y and y is related to z, we can basically conclude that x is equal to z and x is related to z, because equality on real numbers has transitivity property. So there's no need to formally prove that R is reflexive, R is symmetric, or R is transitive, because it seems too obvious. Okay, so since R, which is the relation of equality among real numbers, has all of these three properties, we can basically claim that R is an equivalence relation based on this definition that we presented at the beginning of this slide. So equality is an equivalence relation. Now let's consider another definition. We say, suppose A is a set and R is a relation on A, and R is an equivalence relation on A. Means R has all of those three properties. R is reflexive, R is symmetric, and R is transitive. So for each element A in A, the equivalence class of A, denoted by this symbol, bracket A, is called the class of A, or the set of all elements X belongs to A such that X is related to A by R. Or symbolically, we can say the class of A is equal to this set builder notation, is equal to the set of all elements X belongs to A such that X is related to A by R. Or we can say for every element X in A, we can say X belongs to the class of lowercase a if and only if X is related to A, correct? So that's the definition of equivalence class of A, or class of A, which we define it for every equivalence relation like R, which is defined on a set like A. Okay, so that's a very, very important definition. In the next slide, I'm going to show you a very interesting example of equivalence class. Okay, so in the previous slide, we defined the equivalence relation and equivalence classes of an equivalence relation. In this slide, I'm going to start with a very, very, very important theorem, theorem 834 of the book, which basically says if A is a set and R is an equivalence relation on A, then the distinct equivalence classes of R form a partition of set A. So we defined partition in the previous chapters. I'm not going to define it again, but very briefly, a partition of a set is a set of all the subsets of that set which are both disjoint and not empty, and also the union of all of those subsets build up the original set itself. So in this case, we can say the union of all the equivalence classes is all of A, means they built up to build A, and the intersection of any two distinct classes is empty. We are not going to prove this theorem, but we are going to use this theorem a lot. So let's see an example. Example A312. Consider A as a set of all ordered pairs of integers for which the second element of the pair is non-zero. Or symbolically, let A be the Cartesian product of Z and Z minus set including only zero. So every element, every ordered pair A and B belongs to A represents a rational number. You remember rational numbers were defined in the following way. We say A divided by B is a rational number if both A and B are integers and B is not zero. Here we have the similar thing. We say A and B, which is an ordered pair, belongs to A if A is an integer and B is an integer and B is not equal to 0 because we exclude 0 from the codomain of A. Now, in algebra, we know that these two rational numbers are equal. A divided by B and C divided by D are equal if and only if A times D is equal to B times C, correct? For example, 1 over 2 is equal to negative 1 over negative 2, which is equal to 2 divided by 4, which is equal to negative 2 divided by negative 4, which is equal to 3 divided by 6, which is equal to negative 3 divided by 6, and so on and so forth, correct? So let's define similar relation on A. We define a relation R on A in the following way. We say A and B and C and D, if they are two members of A, we can say these two are related by R if and only if AD is equal to BC, correct? So we define it in a very similar way as the equality of two rational numbers. So this relation, we can prove that is an equivalence relation. I'm going to ask you in the homeworks, in the assignment, in the next assignment, to prove that this relation is an equivalence. It means that you need to prove that it is both reflective, symmetric, and transitive. And then after so you can basically prove that this relation is an equivalence relation. The important point here is that there is one equivalent class for each distinct rational numbers. For example, the class of, or the equivalence class of 1 and 2 is a set like this. You can say the first element is 1 and 2, then negative 1, negative 2, then 2 and 4, negative 2 and negative 4, 3 and 6, negative 3 and negative 6. Why? Because all of these elements will satisfy this relationship, the relationship of AD time AD is equal to BC, correct? This is pretty similar to what we said here when we were saying that all of these rational numbers are equal. So instead of saying that these rational numbers are equal, we can say the equivalence class of 1 and 2 is equal to the set of all of these ordered pairs. So basically, an ordered pair in this example is, corresponds to a rational number, and the relation R that we defined here basically corresponds to the equality relation between two rational numbers. And since the equality was an equivalence relation, here also we have an equivalence relation, and also we have an equivalent class for each rational number. For example, for rational number 1 over 2, we have this equivalence class. Sorry. And based on what theorem 834 claims, we can say that these equivalence classes, the set of all the equivalence classes in set A will partition the whole set, and as a result we can say that we can partition the set of all rational numbers using these equivalence classes.